My name is Jessica New, and I am a HACAST PI from the NASA Jet Propulsion Laboratory. I'm going to be talking about using satellite data to aid quantification and attribution of background ozone changes in the western U.S. I'm going to start by providing some general information about background ozone, and then I will move on to the work we have done at JPL as part of the HACAST team. I'd like to acknowledge my co-authors, especially Kazu Miyazaki and Greg Osterman, who have done the yeoman's share of the work on this project. So what do we mean by background ozone? U.S. background ozone is ozone that's formed from all natural sources, anthropogenic sources in countries outside the U.S., and methane. Background ozone cannot be directly measured and must be determined using chemistry transport models or source apportionment. A similar concept that can be derived from measurements is baseline ozone, and that's ozone measured at remote sites that have little or no recent influence from U.S. domestic emissions. Another important concept is non-controllable ozone sources. The blue arrows in this figure indicate non-controllable sources such as stratospheric intrusions, foreign emissions, wildfires, and biogenic sources. What regions are most affected by background ozone? This is a model-derived quantification of background ozone from Zhang et al. 2011. You can see that background ozone is highest in the western U.S. Monthly mean maximum daily 8-hour average background ozone can exceed 50 ppb on high ozone days. Background ozone is a particularly big issue at high elevation sites. When comparing sites with similar characteristics, high altitude sites always have higher ozone design values. So how can we use satellite data to inform estimates of background ozone? Well, satellites do measure ozone, but it is not possible to use the measurements directly to inform background ozone for two primary reasons. The first is that satellites do not measure surface ozone. They provide either a total column measurement for UV instruments or a measurement that is heavily weighted toward the mid-troposphere for infrared instruments. The second reason is that, as for any measurement system, it is impossible to separate background ozone or ozone from particular sources directly from the measurements. However, as shown in this schematic, we can assimilate satellite measurements of ozone and its precursors into models, and then use the models to quantify background ozone and attribute it to various sources. The JPL assimilation system uses an ensemble Kalman filter approach, which produces fully self-consistent estimates of emissions and atmospheric composition that are informed by multiple satellite measurements. We ingest measurements of NO2 from OMI and TROPOMI, SO2 from OMI, and CO from MOPIT, and those inform the model's NOx, CO, and SO2 emissions. We also assimilate upper tropospheric and stratospheric ozone and nitric acid from the microwave limb sounder, and mid-tropospheric ozone from the tropospheric emission spectrometer, and a combination of the atmospheric infrared sounder and OMI. Together, the measurements of ozone and its precursors inform the model's simulated surface ozone. For our HACAST work, we focused on the fact that complex, non-monotonic changes in emissions have occurred during the satellite period, particularly in Asia. These plots on the left show the changes in Knox emissions from the assimilation system for 2005 to 2010, 2010 to 2015, and 2015 to 2018. And over here, you can see the percent change in Knox emissions by country since 2005. So Chinese emissions increased until about 2011 and then declined again, while those in India and the Middle East have been growing throughout the period. European and US emissions declined relatively rapidly between 2005 and 2011 and then have leveled off somewhat since then. So the question is, what impact have these changes had on background ozone in the US? For our HACAST work, we partnered with the South Coast Air Quality Management District, California Air Resources Board, and other Western U.S. air quality stakeholders. We used the JPL assimilation system to quantify changes in the contribution of Asian emissions to ozone in the U.S., to estimate background ozone using satellite-optimized emissions and stratospheric ozone concentrations, and to generate boundary conditions for regional models. We've run the assimilation for 2005 to 2016 using both the GeoSchem and Merak Chaser models to examine intermodal differences. Throughout the rest of the presentation, I will label Merak Chaser results as TCR2, which stands for Tropospheric Chemistry Reanalysis 2, and is described in a new paper by Miyazaki et al. The control simulation includes assimilation of NO2, SO2, CO, and upper troposphere, stratosphere, ozone, and nitric acid. Tropospheric ozone measurements are not assimilated in this case. We performed a series of sensitivity simulations using the optimized emissions from the assimilation system and holding either emissions or meteorology constant to isolate different effects. In addition to our baseline HACAST work, we proposed the Background Ozone Tiger team to improve the quantification of background ozone in state implementation plan modeling, which is a critical component of the development of stakeholders' attainment plans. The goals were to provide a coordinated set of boundary conditions for ozone, background ozone, and natural ozone for 2016 from multiple global models that are evaluated with or informed by satellite data. Secondly, we wanted to establish best practices for evaluating models with satellite ozone measurements and for evaluating satellite-informed simulations with independent data sets, such as those from surface stations and ozone sondes. We contributed boundary conditions from both the free-running model and the assimilation, both with and without assimilation of tropospheric ozone profiles from Arizomi. We also contributed background ozone estimates from both the standard model and the assimilation. These plots show the evaluation of the control simulation against independent measurements. Here we have the change in surface ozone from 2005 to 2014 from gridded surface observations from the Tropospheric Ozone Assessment Report and from the TCR2 model. You can see decreases in ozone in the US and Europe in both the observations and the model, and increases elsewhere, particularly in South Asia. Over here we have the 2005 to 2010 time series of mid-tropospheric ozone over China and the western United States from the tropospheric emission spectrometer in black, and then from the two models in blue and the two assimilation runs in red. So we have Geoschem on the top and TCR2 on the bottom. The assimilation greatly improves the model's representation of ozone over China, likely because of improved Knox emissions. In the US, where we know the emissions reasonably well, the models perform well even in the free-running mode. These plots show the comparisons between the models and ozone sondes from the California Baseline Ozone Transport Study, or CABITS campaign. The assimilation is particularly effective at correcting mid- and upper tropospheric ozone in TCR2. Our first deliverable was the quantification of changes in the contribution of Asian emissions to ozone in California and the western US more generally. This first plot is for 2012, and it shows the total contribution of Chinese emissions to ozone in and over the South Coast Air Basin in blue. At the surface, the maximum value is just below 4 ppb. The red line, though, shows the increase in ozone in the South Coast region associated with the 20% growth in Chinese NOx emissions from 2005 to 2012. And you can see that it is much less than 0.5 ppb at the surface. The time series in the middle shows the decrease in 750 hectopascal ozone in April associated with decreasing Chinese emissions after 2011. Again, the maximum changes even at 750 hectopascals are considerably less than half a ppb. On the right, we have the change in 750 hectopascal ozone over the South Coast Air Basin from emissions in China, India, and the Middle East relative to 2005. The top panel shows 2011, and we see the increase in ozone from China with a maximum value of about 1 ppb at 750 hectopascals. And I'm not showing it, but that's about 0.3 ppb at the surface. In 2016, we see the decreased contribution from China, but we don't see much of an increase from either India or the Middle East despite large growth in emissions. Much of the ozone from these locations is transported to the south of the US. Our second deliverable was the production and evaluation of satellite-informed boundary conditions for 2016 to the EPA Office of Air Quality Planning and Standards, as well as several regional and local air agencies. These plots show our evaluation of the 2016 model simulation that we used to generate the boundary conditions. On the left is the correlation of daily 8-hour maximum surface ozone for April with gridded surface observations. The free-running model is shown on the top and the assimilation on the bottom. Here's the difference in the correlation, with blue values showing a better correlation for the assimilation and red values showing a decreased correlation. The correlation has improved most everywhere in the assimilation except in the south-central US. On the right is the difference in bias between the assimilation and the free-running model. Both the free-running model and the assimilation are positively biased almost everywhere, but the assimilation is more positively biased in most places. We are still working to determine whether the additional assimilation of tropospheric ozone measurements from Arizona will reduce the bias in the assimilation. Since we were particularly interested in improving the representation of long-range transport in the boundary conditions, we also compared the model to satellite observations in the Western Pacific and ozone sondes from the Cabot's campaign along the coast of California. These plots show 680 hectopascal ozone averaged over April 21 to 30 of 2016. This plot now shows Arizona at this level within the Western Pacific boundary box shown here. You can see that there is enhanced ozone in the central and southern portions of the box that is not captured by the free-running model. The assimilation, however, reproduces these plumes quite well, despite the fact that no tropospheric ozone measurements are assimilated. The plumes are generated solely by the correction of precursor emissions in Asia. Here we show that the assimilation also improves the representation of upper tropospheric ozone variability relative to the Cabot sondes. Again, we expect that further improvements may be seen with assimilation of Arizona. Our third deliverable was satellite-informed background ozone estimates, which we are providing to EPA, the California Air Resources Board, and other stakeholders. To estimate background ozone, we used the optimized emissions from the assimilation and zeroed out U.S. anthropogenic emissions. This plot shows the daily average background ozone for April 15, 2016. This is the monthly mean background for April, and this is the percentage that background ozone contributes to the total ozone at the surface for April. Here we show 2016 ozone over California for the entire year. You can see that background ozone peaks in spring and makes up almost all of the ozone at 750 hectopascals for more than half of the year. It contributes about 40 ppb on average at the surface during spring. Our background ozone distributions and magnitudes are consistent with previous model-based estimates, with about 70% of the ozone in the western U.S. coming from background contributions. We're still working on evaluating differences in background ozone between assimilation and free-running models for both model versions. I wanted to close out by talking about what I am excited about in the future. This figure shows what's called the Atmospheric Composition Virtual Constellation, where we have geostationary instruments over Asia, the US, and Europe, and LEO instruments with new and exciting capabilities providing global measurements to tie them together. For example, this is formaldehyde from Tropomi with 7 by 7 kilometer resolution and low noise that greatly reduces the need for averaging. Along with solar-induced fluorescence from Tropomi, it should provide new insights into the emission and oxidation of biogenic VOCs. These are tropospheric ozone retrievals for a single daytime overpass of the Crosstrack infrared sounder processed as part of a new ozone trends initiative at JPL. We've never before had infrared measurements of tropospheric ozone with the coverage, spatial resolution, and low noise that is now available from CRIS. We can also retrieve species such as peroxyacetyl nitrate from CRIS, which plays a critical role in ozone and secondary organic aerosol formation downwind of sources including wildfires. By harnessing these satellite measurements together in the JPL assimilation system, we can provide air quality managers with new insights into the processes controlling the formation and transport of pollutants and inform strategies for effective mitigation.